Hi there. Welcome back to Core C++ Part 9. In this part, I'll be talking about lambdas and other expressions. So we've gone over lots of the clauses of the core C++ language, all the way from templates to overload resolution. But I've been having to answer a lot of questions about expressions and especially lambdas recently, and I realized I haven't really talked about those in depth. So before we get to lambdas, I want to talk a little bit about the basics of expressions in C++. So we all know that we can write, all sorts of complicated things, but I sometimes get the sense that a lot of programmers, they just sort of dive in and they write based on examples that they've seen, and they haven't really delved into what makes the core language tick. And so some complicated things seem mysterious to them. And I approach programming in a very different way. What I do is I look at either the documentation for the library that I'm using, or in this case the standard, and I try not to write things unless I actually know what makes them work at a very low level. And this means that I rarely get surprised by complicated surprises, although it still happens, even to me. So one thing about expressions is how they're parsed. So imagine I've got something like, x plus y times z, or a times b plus c. So everybody basically knows that y times z here will happen first, and so that it's equivalent as if I had put parentheses around here. And that's precedence. But then people sometimes also hear about associativity, and they'll mix up the concepts, and they're not quite sure exactly what will happen if things get more complicated. And we can write, even in C, things like, say, dereference dest plus plus equals dereference source plus plus. This is a very complicated expression. There's a lot of things going on here. This is, in fact, idiomatic C. It basically says blast through with source and dest pointers, or these could actually be iterators in C++, and write through to whatever they point to. But C and C++ have to parse this, and they do this with precedence and associativity. So this is not outright stated in the standard. They don't give a nice little precedence table. In fact, they have a helpful note that says, oh, by the way, the precedence can be deduced from the grammar. But if you look at clause 5 expressions, they list things in order from highest precedence down to lowest. The lowly comma operator is all the way down here. What I actually have done is I made a little Excel spreadsheet that I printed out, and I hang it underneath my monitor. So just in case I have, let's see, I put it on my desktop. Whenever I want a quick reference for precedence and associativity, I can just look at what's taped to my monitor. I even forgot about this until we had an intern ask, hey, what's that thing on your monitor? And I'm looking on the screen, and of course he's referring to the thing that's taped below. I had barely even noticed it. This is actually not completely accurate because the conditional operator is actually kind of strange. It can be thought of almost as having the same precedence as the assignment operators. And I left off things like cas and so forth. But this is essentially pretty complete for C++. It's even got a couple strange operators here that I'll talk about in a bit. And the way I organize this thing is it puts the highest precedence, I just numbered them. So the highest precedence is 1 up here. And most things have left to right associativity, but a few special things have right to left, and I encoded that here by highlighting them in red. And this is important when looking at rather complicated expressions. So the quick primer here is if I have something like, let's say, x plus y, say minus a times b, and let's say divided by c, something like this. And let's actually say w, why not? So if I've got a long expression here, this whole thing is a statement, the semicolon, but the expression is what goes here. And we can put expressions in all sorts of places in C++, like in for loops and other places, function calls. Every operator has a precedence and associativity, but the precedence is what matters most. Things with higher precedence bind more tightly, and they are grouped together before associativity is even considered. Associativity only comes into play when deciding what to do with operators of equal precedence. So the multiplication operators, and that includes times, divide, and modulo, which is the percent symbol, which we don't use that often, these have a higher precedence than the addition operators plus and minus. So this stuff will all bind more tightly than the pluses and the minuses. Then, when it comes to figuring out whether this should be evaluated, whether the result of this should be fed into the multiplication, the associativity matters, and both the multiplication and addition operators, and times and divide and all that stuff, these are left to right associative. So what that means is that A times B will be evaluated before being divided by C. And if I had something like A divide B times C, in this case, this would happen first, and then this. Whereas if you look at this, you might just naively think, oh, it's going to be A divided by B times C. No, it's left to right associative. And then when it comes to these addition operators over here, we'll add these first, and then we'll add this, and then we'll subtract the whole thing. So we can always add extra parentheses to make it very, very clear what we want, or to change the usual rules, because of course parentheses override the rest of the precedence. So C and C++ are kind of famous, infamous perhaps, for having precedence that is kind of weird. The precedence of the bitwise operators versus the logical operators is widely agreed to be bad. So whenever you write an expression with the bitwise operators, you should strongly think about parenthesizing it. Otherwise, you may not get what you expect, especially if you're mixing them with the addition operators, which have much higher precedence. Otherwise, the precedence is pretty logical, and most of the time you don't need parentheses. I typically tend to avoid writing unnecessary parentheses, so the necessary ones stand out. Although over the years I've transitioned to writing a few more parentheses than is strictly necessary, especially when it comes to like the logical operators. But like and binds more tightly than or, and multiplication binds more tightly than addition. So I'm not going to parenthesize something like A plus B times C when I want B times C to happen before the addition. So that's how expressions are parsed at compile time. But then there's the notion of, well, what happens at runtime? And that's very different. So imagine that instead of just variables here, if I've got something like f plus, say these all return ints, g times h, okay, so these are function calls. And of course, the function calls bind more tightly than addition and multiplication. So the precedence tells us that the result of multiplying the return values of g times h will then be added to f and not the other way around. This says nothing whatsoever about the order in which f, g, and h will be invoked. And C++ has a rule, which I may have mentioned in the past, but now we're going through all of expressions. And this is actually hiding all the way over in clause 1 general, at least in N3485, which is the working paper that I'm looking at. Paragraph 15, and this is, by the way, this rule is in C++ 11, but it goes all the way back to C++ 98. And in fact, this is also true in C. This says, except where noted, evaluations of operands of individual operators and of sub-expressions of individual expressions are unsequenced. This says that when C++ sees something like this, it can evaluate things like function calls in any order it likes. So given this, it could evaluate g first, and then f, and then h, and then it will take the integer results of these things and then multiply them and add them. So in the end, you will get what you asked for, but the actual order in which these function calls are evaluated is unspecified. And by the way, when C++ says unspecified or unsequenced in this case, there's actually a helpful note in C++ 11. It says if it's evaluated more than once during the execution of a program, such unspecified order can be different every time it's evaluated. So the compiler is not required to choose some particular order and then fix that for the lifetime of the program. It could be different every single time that expression is executed. You could imagine that it could be inlined at different call sites and the compiler chooses to reorder stuff. The principle behind this is that an optimizing compiler may look at something like this and say, oh, if I sequence, say, the multiplication before the addition, or if I call this function before that function because I've inlined their guts, I can keep the processor more busy because the compiler has a pretty good understanding of the kind of processor it's going to run on, especially if you tell it specifically what architecture to tune for. And it can decide that, oh, if I reorder the instructions this way, I'll get you a better result. That's why C++ leaves this unspecified rather than fixing a particular order. Sometimes beginners will come, especially from other languages where things are more tightly specified, and they'll expect a certain order, like left to right or right to left or inside out, and C and C++ just don't specify it at all. Of course, some things are specified. For example, if I have something like all of this being given to a function meow, there is, fortunately, a rule in C++ that says all of this will at least be evaluated before the meow function is called. So you're guaranteed that the arguments to a function at least have been evaluated before that function itself is called. And you get guarantees like function evaluations will not be intermixed. It would be very weird if in a single thread, F and G, their bodies could be executed interleaved. That's weird. C++ at least forbids that. There's another rule that comes into play, and it's actually mentioned in the same paragraph when people start to write complicated expressions. And this rule I refer to as the multiple modification rule. And again, this goes all the way back to C, although the language you're looking at here is slightly newer than C++ 11. And it says, somewhat obscurely, if a side effect on a scalar object, and what it means here is like integers and floating point things and pointers, so not like C++ objects, but just built-ins. If that side effect is unsequenced relative to either another side effect on the same scalar object, so like two writes, or a value computation using the value of the same scalar object, that means a read, the behavior is undefined. So when C++ says unspecified behavior, it says something has got to happen, it's got to be reasonable, like you've got to execute F, G, and H in some order, but I'm not going to say what, and it could change. And if C++ says something is implementation defined, what that means is that the implementation, the compiler and library, need to pick something and document it and do that reliably. For example, the size of void star is implementation defined. So an implementation picks, okay, it's either 4 bytes or 8 bytes or whatever, and I'm going to document that and fix that for a particular configuration. But when C++ says something is undefined behavior, that means the standard places no requirements on a program that happens to trigger that. In fact, it even goes backwards in time. So if a program triggers undefined behavior at any point, the standard throws up its hands and says, hey, I'm not going to require the program to do anything. And the implementation, the compiler and library, can make it crash or behave bizarrely or do exactly what you expect for maybe 5 years. And then it goes and crashes after you shipped it to some customer. Undefined behavior is really bad. And so this multiple modification rule applies to complicated expressions, and the standard has a helpful example down here. Whenever you start to try to write to something more than once in a single expression, you start to violate the multiple modification rule. And the simplest example is I equals I plus plus. Okay, this tries to write to I, incrementing it, and then it tries to assign to I. And this happens in a single expression, and there's no sequencing. A little bit of a tidbit here. In C++ 98 and C++ 03, the standard talked about sequence points. The idea was that the standard would specify certain places at which all the side effects had to be complete, and things separated by sequence points had to be evaluated in a certain order, but between sequence points, things would just be unspecified. In C++ 11, that has been changed to this notion of sequenced before and unsequenced, which is more useful when talking about correctness and multi-threading. But it's still the same general model as long as you don't look very, very closely. So you can still think in terms of sequence points if you were introduced to that. Or you can think in terms of sequence before if you'd like to live entirely in C++ 11. So in something like this, you're not guaranteed that this will be evaluated before this. In fact, this is undefined behavior. The program can crash because the optimizer can do things that will make this completely invalid. A few things do guarantee order of evaluation, and those are the logical AND operator, the logical OR operator, the comma operator. So if you have something like, say, f of I++ and then g of I++, as long as the comma operator has not been overloaded, you're guaranteed that this will be evaluated, as if there was almost a semicolon here, then this will be evaluated, and then this will be returned. The comma operator is pretty strange. In fact, I had to mention it to another developer pretty recently. Most of the time, you do not want to just glue together expressions with comma operators, but there are a few cases where it's useful. For example, in a for loop, you might have for, and then you mess with a couple indices, so you're initializing stuff here, and then you have, as long as keep going, some condition here. And say you've got like an I and a j index, and you want to increment them both. Well, you can't just say I++ semicolon j++. You've got to fit a single expression in the third part of the for loop. And here you can use a comma operator. You could say, well, I should probably say ++i, because we should prefer pre-increment in C++, ++i, comma, ++j. That's a single expression, and we can stick that in a for loop. But try to avoid doing too much in a single statement, because both of this unspecified order of evaluation and especially the multiple modification rule, if you ever look at an expression and you're like, man, I don't know exactly what this is going to do, split it up into multiple statements. Don't try to cram too much. Even if you can point to the standard and say, yes, this is absolutely well specified and I know what it's going to do, if it's too complicated for humans to read, you probably shouldn't be writing that. Simplify it. In general, like deref des++ equals deref source++, that should be like the highest level of complexity you're aiming for. Something that is, yeah, it's complicated, but it's idiomatic and people understand how it works. Anything beyond that, try to avoid. So that's what I wanted to say about expressions in general. Let me mention, as we go into Lambda expressions, a little bit about how pointers and pointers to members work, because pointers to members actually have their very own operators. So actually, I may as well, I can scribble this in Visual Studio. So I've got some stuff here. I won't even try to compile anything. So imagine that we've got a couple functions. Actually, I will try to compile something. Let me just comment this out. Okay. So imagine we got a couple functions. Void meow. It's going to meow at somebody. And then another function that makes a different cat noise. Here I'm running Visual Studio 2012 Update 2. Imagine I've got, some for loop, and I is 0. Okay. So I could say, if, I mod 2 is equal to 0, then I want to call meow instead of purr. Okay, that's simple. But imagine that I've got this in, some other function, woof. And I want to pass it. Actually, why don't we do that? Okay, I want to pass it a function to invoke, and then I want to call it. And this is achieved with function pointers, which you've probably seen. So it's a little strange if you've never seen it before how to declare a function pointer. The declaration has to be read inside out, and in this case, it would look like this: pointer fp. Okay, the way to read this is fp is a pointer to a function taking nothing and returning void. And then I can initialize this with the address of a function. Like here I could say address meow. And then I could call woof, and here it'll have a parameter like this. And then inside here I can just invoke it. I can say, okay, deref fp, and then invoke it. And here I'm parenthesizing the dereference because the dereference operator actually has lower precedence than the function call operator. I could show it in the standard, but my table makes it a little clearer. Dereference is lower precedence than the function call operator. So if I had written, instead, if I had written fp pren and then dereference, that would call, that would say call fp and then dereference its result. But here it returns void. I don't want that. So I can do this. And the nice thing about function pointers is that they're variables. So I can determine them at runtime, I could loop, and I could say, okay, for every odd one, initialize it to address per, or so forth. So I could feed woof with, oh, I said fp, and then this should print it out. Oh, I don't want to close main there. And compile and run. So this is function pointers 101. I was able to give, here I get it printed out, I was able to give a pointer to a function to invoke, and I determined that at runtime. So I could have, you know, int argc something here, and then test that, or switch on user input and then feed that to woof. There's a few syntactic shortcuts you can take. This goes all the way back to C. C does not require you to dereference a function pointer before you invoke it. Instead, you can say, and I highly recommend it, you just say fp, paren. The notion here that C and C++ have is, yeah, it's a pointer to a function, and I'll allow you to, you know, dereference it and then call it. But if you just put a function call operator right next to a pointer to function, what else could you be trying to do with this thing? I'll just call it for you. I'll auto dereference it. So this is a syntactic shortcut, but it makes life easier. I recommend doing that. The other thing that C++ and C let you do is, instead of saying address meow here, you can just say meow. And a function will decay into a function pointer whenever it's required to. So in this case, I can initialize a function pointer by just saying equals meow. The type of meow, it's actually a function type, but it'll decay into a pointer to function. And understanding decay is necessary when you start writing complicated template code, that sort of thing. So function pointers, most people have seen them. Pointers to members, though, are one of C++. They're C++ specific, of course. They're not in C. And those can be a little confusing. They have their own special operators. So imagine that I have a struct x, okay, with a couple member functions, void meow. Actually, why don't I just return some ints? Something like this. And why don't I make life a little more interesting? I'll add a third one. Per 22. And then something like woof int n const n times 3. Then a couple data members, int x, int y. So here, imagine that I have an object of type x. I say xx, and let's see, it is an aggregate, so I can actually initialize it with braces. 100, 200, like this. Okay. Sometimes, and this occurs when you write generic code, you'd like to say, okay, I've got maybe a whole bunch of structs. Here I've just got one particular x. But you might say, okay, actually it's confusing here that I have data members called x and y. I'll call them a and b. You might say, I want something that, given an x, will select its a data member, or select its b data member, or call its meow function, member function, or call its per member function, but I don't want to pin it down to a specific object, and that's where pointers to members come in. And what you can say is, you can say, okay, I'll show you pointers to member data first, and the declaration, it looks strange the first time you see it. PMD equals address x a. So this here, it declares and defines PMD is a pointer to member data. And its type is pointer to member of x, that's of type int. And then you have to say address x :a to get a pointer to member of this. And the address of is actually required here by the standard. Unlike function pointers, you cannot omit it. And then you can apply it to an object of type x by saying, okay, let's see out, and then put an expression here. And I want to say x dot dereference. This is a single operator, PMD. And this says, okay, I've got this notion of a pointer to a member of x of type int that will select its a data member. I'll give you an actual object here. And this will select its a, which is 100, and print that out, assuming I've not made some horrible mistake. And let's try that. And, oh, I made some horrible mistake. What did I do? Let me make this bigger. X followed by, oh, I didn't close it with a semicolon. Thanks, Visual Studio. Got to push a semicolon after my struct. Save. Okay, let's try that again. Awesome. So it selected the A data member, which I had initialized to 100. I could have said, okay, PMD points to address XB, and then select the 200. And I can give it any object here or a reference to an object. But what if I have like a pointer? I could say, imagine I've got some X pointer here. X pointer P is address of this X, or anything. And then I could say P arrow dereference. This arrow dereference is a single operator. And if I compile and run, I'll get the same output because I'm still selecting the A data member. There we go. These operators have their own level of precedence. Pointer to member operators, it's kind of strange. I actually believe that their precedence is wrong. I think that they should be at the highest level of precedence. I've never understood why they're here. It's always seemed to me like an unforced error in C++. Maybe there was some rationale, but it's just something we got to live with because there's no way it's going to change now. They bind more tightly than multiplication and definitely higher than shifting, which is why I don't need to parenthesize anything when I'm saying cout. But in certain cases, especially when I want to invoke a pointer to member function, it needs to change. So that's pointers to member data. If I've got a pointer to member function, imagine that I want to say, okay, let me get this up here. I want to say PMF, okay, is a pointer to member of X that takes nothing and returns int. I have to declare it inside out, so it ends up looking like this. Address X per, like this. So PMF is a pointer to member of X that takes nothing and returns int. I can also use type defs to simplify this. I would put a type def where I would declare a variable, and then I could just say PMF underscore T or whatever. But here I'm writing it all inline. And then if I actually want to invoke this, I have to say parenthesis x.deref PMF, and then call it. The reason why I need to parenthesize this is because this pointer to member operator has a lower precedence than the function call operator. And if I did not have the parentheses here, the language would say, oh, you're trying to directly call PMF, but you can't do that because I don't have an object to call it on. That's why you need these extra parentheses here. Like I said, I kind of think this is less than ideal in C++. But if I put the parentheses there, I can compile and run, and I get 22, which is what the per function returns. And pointers to member functions can be const qualified, just like member functions themselves can be const qualified. So if I have, say, I want to take the address of woof here, woof is a member function taking it, returning it, but the member function itself is const. That has to be part of the pointer to member function type. So I actually need to say int here, come on, int, and then say const. And now this member function has the right type. And if I save this and then run, I did something wrong. What did I do wrong? Oh, I didn't call it with arguments. I need to give it an argument, and we will say 5. Save and run. There we go. So I can invoke even const member functions as long as I get the type right. Now in C++ 11, we have auto, and auto is wonderful. It allows you to say, okay, I'm going to declare some variable, and I just want you to make its type the same as the type of the thing I'm initializing it from. Because the compiler already knows what the type of address xwoof is. So if you've got, like, you're saying int n equals 100, it doesn't buy you anything to say auto n equals 100. That's actually one more character. But if the type is complicated, like an iterator type, or here a pointer to member function that's const qualified, saying auto can be a real time saver. So you could just say auto PMF, because the type of this will just be, okay, that's going to be PMF's type. So this will also compile and run. Awesome. So now, let's see. Yeah, why don't we talk about Lambda functions? So Lambda functions, you can think of them as a lot of things. Some people say anonymous function. Those people are bad and wrong. Some people say closure. They have a little more justification because closure actually appears in the standard. I just don't like that terminology. So I'm going to stick with Lambda. Lambda, yeah, it comes from functional programming. You can just think of it as a meaningless word. Yeah, it comes from Greek. It has a meaning in functional programming. But if you're used to C++, you're not familiar with the Lambda calculus. And I just view that as sort of the wrong mental model. I've noticed a lot of programmers looking at Lambda expressions, they think they're like mysterious, and they're actually quite simple. As long as you're familiar with what motivates them, and what motivates them is using them with the STL. So I'm going to talk about the core language, but the motivation here is really algorithms. So imagine, let me get rid of this stuff. Okay, I've got all my usual includes here, but I don't need any includes to use Lambda expressions themselves, a part of the core language. But if I want to use them with, say, vector or algorithm, I need to include those headers. So here I've got a vector string, and imagine that I want to do something with them, like print them out. Okay, that's easy. But what if I want to like sort them? I could say, okay, I want to sort v begin v end, very easy. This will sort them by default in less than order, which is lexicographic. The end. I shouldn't type while I talk. Okay, that should be good. It's still giving me squiggles. Hopefully that's not a problem. I did something bad. Sort v begin v end. Okay, I'll look at my error. Missing semicolon before dot. Oh, I nuked my main. That would be bad. There we go. Much better. And then compile and run. Awesome. So I can sort them in lexicographic order, dictionary order. So cat comes before puppy because C comes before P. And if I had words starting with the same letter, they would be tie broken. Nice. But what if I want to customize my sort? So I could write a function that would take two strings. For example, I could say, okay, bool compare length, or compare size, taking two strings, const string ref L, const string ref R, and then return L size less than R size. So here I'm only looking at the sizes. I'm not looking at what they're doing. And then I can give a custom comparator functor, which you may remember from the STL videos, if you watch those. And I could say, okay, address compare length, or as we saw, because I want a pointer to function, I don't actually need to say address of. I can just give a function directly, and template argument deduction will say, okay, you must mean a function pointer, because it will actually perform decay, because functor here is taken by value. So I can do this, and this will compare them in order of length. So ox here will be considered the least, because it's the shortest. And then cat and dog there are the same length, and sort is not stable, so they'll be printed in any order. Here they happen to be printed cat first, but it could have been dog first. I would need to say stable sort to preserve their order. So that's great. But what if I look at this, I had to write compare length all the way up here, which is far from the point of call. What if I just wanted to define it inline? Well, C++ still does not have local functions, so I couldn't like put this in main. And if I wanted to put state in here, functions can't really store state. Yes, you can have static variables inside a function, but they're not really what you want, because there's only one. It exists for the lifetime of the program once it's been initialized. So if you've got multiple, say, threads simultaneously calling a function with a static anything, like, you know, static int x here, C++11 says that its initialization will be thread safe. That's called magic statics, or that's what I call it. But actually using it would not be protected. So if you say ++x inside this function, you'd have multiple threads trying to simultaneously increment a single x. That's not cool. So you really should not try to stick state inside functions. C++ has a way to do that. It's called classes. Classes are wonderful because I can write a struct here. Okay. Imagine that I say, okay, struct, and let me change the sort call here. So I want to do a transform, v begin, v end, and say emphasize, like this, and then give it a string. Okay, and I need an extra parenthesis. Okay. So I can say, okay, I've got a struct emphasize, and yeah, it should really be a class. Okay, I can make it a class. When I'm writing examples, usually I don't worry too much about access control because it's not production code. I could say private, I'm going to have a member under a string, member stir, this. I'm going to need a constructor. I need to make it explicit because I probably don't want to implicitly construct these. string ref s, initialize mstr to s, like this. And then I'll have a function call operator using operator overloading, which I have not actually done an episode about, but it's relatively simple enough. If I'm going to take an input, string as input, I could say input here, it should be const. I will return, I just want to concatenate the input plus whatever my member string is. This here. That looks good. Oh, and I need to give a name to my operator. Okay, so this is it's a function call operator that takes a string as input and then concatenates whatever string I've stored. So this is a very simple example of a stateful function object. A function object is just anything that's callable with operator paren. So that could be a function itself, or it could be an object of class type. And here I'm storing state. And here I just want to add on a couple exclamation marks. And why is it squiggling me here? I added a semicolon. And I have algorithm. That should give me std transform, v begin, v end. Oh, it needs to write somewhere. I want to do this in place. Ah, it didn't even need to compile there. Okay. And emphasize, that's the right name. That should not be squiggled. I think I'm putting something in the wrong order. Can I? Oh, I didn't make the constructor public. Classes default to public access control. See, this is why I should have set a struct. There we go. I hate auto formatting. I usually write into plain text editors, I'm sure I've mentioned. Okay, so now my function call operator and my constructor are public, so everything should compile. Awesome. Okay, so now I have concatenated a couple exclamation marks to every string here. So this is an example of a stateful function object. C++ has an excellent way to do this. It's just a data member of a class. Everybody knows how classes and data members work. And yeah, operator overloading gives this member function a funny name, operator paren, but then it's used just like a normal function inside transform. This is really wonderful when you look at it. But we had to go write this verbose function object. We had to give it a constructor, give it a data member, give it an operator paren. So in C++ 11, Lambda Expressions allow you to write something in your source code at the point of call to say this transform functor that will then construct a temporary object, which the standard refers to as a closure object, but I usually just say Lambda object because it's made by a Lambda expression. And that is identical to what you could have written by hand. The compiler is not doing anything magical here. It's simply allowing you to do this very quickly. It's equivalent to structs with data members and constructors. So instead of emphasize here, I could write a lambda like this. Let me first write a stateless lambda. So I've blogged about this before, but some people like to watch videos, so I'm going to assume that you've not seen me blog about lambdas. The way that I write a lambda function, I'll put this on its own line here, is I need to start it with a lambda introducer. So if I put empty square brackets here, you can think of this as the name of a function. And then I put a parameter list, and I say, okay, this needs to take a const string ref, and here I can just call it s, and then I can just say, okay, brace, here's just a normal function body, and I can say, okay, return s plus, let's concatenate something to it, some exclamation marks, like this. So this is a simple lambda, and then this paren semi here belongs to transform. So you can think of this as equivalent to writing a struct, and this one would not have any data members, with a default constructor and then a function call operator that returns this thing. And then if I save this and run it, I'll get my 3 exclamation marks concatenated. This is really nice in terms of convenience and in terms of readability, because what I want to do is written right next to the call site. Now, if I wanted to use this over and over, maybe then I should think about making it like an ordinary function or even a name struct. But if I'm only going to use it once, then I can just put it here. I can, however, lift it out if I want to use it repeatedly with auto. So the thing about Lambda expressions is that the Lambda objects they return have unspeakable types. You can think of this as making a temporary type like Lambda 1, although in the debugger you can actually see the real type the compiler is giving it It is currently in VS 2012 constructed by hashing the guts of the lambda and a little bit of the context. And there's all reasons why we use a hash instead of just numbering them lambda 1, 2, 3 as we used to long ago. But it's an unspeakable type. In ordinary code, you can't write it. But you can ask the compiler to basically do it for you. You can say, okay, auto lambda, or auto emphasize, or whatever I want to call it, equals lambda expression. And the compiler says, okay, this makes a temporary function object, and then I'm going to copy initialize lambda from it. In practice, you'll get copy elision, and you'll just directly construct this thing. And then here I can just pass lambda. This would be useful, for example, if I wanted to use the same lambda in a few function calls in a row without having to repeat it every single time. I can just write it once and then use it over and over. So this, if I save, should compile and run, and I get exactly the same output. Awesome. Now you'll notice in my lambda function here, I didn't have to write a return type. And that's because in C++11, lambda functions get something special. This was actually given only to lambda functions, although the committee was thinking about granting this to functions in general. And that has actually happened, I believe, in C++14, although I'm still getting familiar with the standardese. But as of C++11, only lambdas get the special treatment. And that treatment is, in C++11, the rule strictly said, by default, a lambda returns void. So if you just want to do something, but you don't want to return a value, then okay, you get a void return type. But if your body consists entirely of a single return statement, so return stuff, and that's the only thing inside your braces, then the lambda gets an automatically deduced return type of whatever the type of the return expression is. So here, because the type of return s plus bang 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 is a stood string, this lambda expression has a return type of stood string. Now, I could have said the return type explicitly. Now, I have to use slightly different grammar to do that. Here, let me get rid of, actually I can just leave it here. This would be equivalent if I put this lambda expression inline in the transform. I'm just lifting it out and giving it a name. The place that a lambda function's return type goes is actually after the lambda's name itself. And there's a reason for this. The reason is tied to how C++ is parsed. And actual compiler devs could explain this better than I can. Basically, C++ is not really prepared in the middle of something like a function call expression to just start seeing types mentioned, like int or string. It would be extremely difficult, if not impossible, to parse C++ like that. So the way that lambda expressions were specified is that the compiler sees this lambda introducer first, these brackets. After that, then it knows that whatever comes after is a lambda, and is prepared to see certain patterns. And what C++11 does is you have a late specified return type or a trailing return type here. And here I can say, okay, this returns a stood string. There we go. And that is what would automatically be deduced. But if I had extra statements here, C++11 would require me to specify the return type being string instead of getting automatically deduced. This has actually changed in C++14. Things are evolving quickly. And this is actually related to an extension that we added to Visual Studio. Imagine that you had multiple return expressions. So here I'm just going to write some code that won't compile. If I had something like if condition, then return this, otherwise return something else. The body of this lambda is no longer a single return statement. So C++11 said that it would not get an automatically deduced return type, and I would need to explicitly specify it. And that's a little less than ideal. Programmers would look at this and they say, but I've got multiple return statements, but all of their types are identical. Actually, in this case, they're not identical. Haha. But if I said something like s plus something else, now they are identical, because here this is a stood string and this is a stood string. So C++14 has already changed its rules, and it says, okay, you can now have multiple return statements in a lambda, or a return statement in other stuff, and you'll still get an automatically deduced return type as long as all of the types in the return statements are identical. And this was actually implemented as an extension in Visual Studio. So if I get rid of this, and if I make the string here, let me say if s size is greater than 4, then I'll say s plus some question marks, and I don't think I want a trigraph here. I'll just say 2 question marks. Okay, like that. This is not valid C++11 because it gets a return type of void in C++11, but in C++14, the compiler says, oh, okay, this is a string and this is a string. Okay, your return type is stood string. And VS actually already supports this. Let's see. Yes, it does. So things that are long get the exclamation marks, things that are short get the double question mark. So we've implemented that particular feature earlier than the rest of C++14. Now, you can stick other things inside these square brackets, inside the Lambda introducer, and those are called captures. And this is one of the reasons why I really don't like the terminology closure, because if you look in functional programming or say on Wikipedia, the term closure comes from the idea of a function having sort of an enclosed environment. It basically creates a copy of the environment that it saw when it was created. And I find that to be unnecessarily confusing. Remember, this is just stamping out a plain old, it's just a class with data members. And captures are a way to initialize those data members. And in C++, we distinguish between data members that are values and data members that are references. And the capture syntax allows you to distinguish that. So let me change this here because I don't need these return types anymore. Imagine that I said something like, I don't want caps lock. Let me see here, put return s plus, I'm going to say suffix, okay? And imagine that I've got something like a string suffix here, and construct this from just maybe a single exclamation mark. Okay. So if I try to compile this, it will not compile because this lambda is stateless. When I have empty square brackets, what I'm doing is I'm stamping out a class that has no data members whatsoever. So I can have arbitrarily complicated code in the body of the lambda, but I can't refer to any data members, and I can't refer to anything that appears to be in scope. Because if you didn't know anything about lambdas, you might look at this and say, but I just declared suffix up here. How come I can't refer to it here? And if your mental model is that lambdas just stamp out classes, function object classes, and then create a temporary object, you'll see why. It's because the code that the lambda expression here is stamping out is really, say, up here. It's in some location that's outside of main. And there, it only has access to its data members, and it can't see suffix here. If you have global variables, lambdas can see global variables, but you really should not have globals in your program. It certainly can't see a local variable to main. We have to capture it in a data member for that to happen. So I can capture things in two ways. I can capture them either by value, making a copy, or by reference, and I'll refer to the original. So if I say suffix here, I have to name a variable in order to capture it. This is, okay, I'm going to make a member variable which has an unspeakable name, but whenever I say plain suffix here, I'm referring to that data member of the lambda and not the one out here. It was created by copying. So if I compile this, I'll get my exclamation mark concatenated. And here we go, I get that single exclamation mark. IntelliSense here, when I highlight over, actually I had to go like this, it's helpfully highlighting all the occurrences of suffix, but this is not quite correct. Yes, syntactically these are all the same, but at runtime, the suffix here is a member variable of the lambda. So if I modify the original thing, the local variable in main, that will not be reflected in the lambda. So here I could say, I could assign the suffix before I actually invoke the lambda. Suffix is something. Okay, so at the point of the transform call here, suffix is something. It's not this exclamation mark. But if I compile and run this, I still get an exclamation mark concatenated. That's because the lambda captured a copy of this local variable, and so subsequent modifications are not reflected. Now, sometimes you want this, especially when writing multi-threaded code, if you're using like async, as a lot of people now are. If you're shipping this off to another thread, you don't want to worry about lifetimes. In particular, you really don't want it, a function object like a lambda to be referring to local variables that might be modified on the thread, the parent thread that launched it. You often want to capture everything by copy, and those copies become independent of what they were initialized from. And then they can be freely inspected by the child thread without worrying about what's happening to them in the parent thread. So often you do want captures by copy, but sometimes you don't. Sometimes you want to avoid the expense of actually copying these objects. Maybe it's a multi-dimensional vector and it's a megabyte and you don't want to copy that. Or maybe it's something that's not copyable, or you want it to reflect updates. So you can capture things by reference, and you do that by just saying ref suffix. And this all comes from the grammar and the standard. If you look here, I'm looking at N3485 because this is before some C++ 14 changes in the committee draft N3690 that have not been implemented in VS 2012. You can see here it specifies lambda capture, and captures can either be a plain identifier or ref identifier or this. And ref identifier is then specified to create a data member of reference type. So if I write this, let me kill that, save this. I'm going to initially say suffixes and exclamation mark. I'm going to capture it by reference. Then I'm going to modify it to something. So here I get different output when I compile and run. Now I'm concatenating something here. And that's because I still have a data member in my lambda, but that data member is of type string ref, and it's bound once and for all to the local variable out here. So updates are reflected, and I could even modify it from within the lambda, and then those modifications would be reflected on every subsequent thing. For example, I could store a reference to an int, and I could increment that int whenever I'm invoked. And then at the end, in fact, why don't I do that? I could say int n is initially 0, and then here I would say plus plus n. I would need to capture it by reference, ref to n, and then at the end here, actually even before the loop, I could print out n. Here I would expect it to be invoked the same number of times as elements in my vector. This is totally allowed by the STL because although I'm modifying n, I'm not like resizing the vector during the transform. That would be weird and that would trigger undefined behavior. Here I'm just incrementing a counter. So I can compile and run this. And here I get 5 printed out because this function object was invoked 5 times and incremented n 5 times. So this is a way for lambdas to communicate directly with local variables from where they were launched. And it's just a reference data member. There's no magic here. No magic whatsoever. It's not like, and by the way, lambdas, they only capture what they need. So lambdas, for convenience, they have this notion of a capture default. So if I'm mentioning a whole bunch of variables and I want to capture them all by reference, I don't need to mention them all in the lambda introducer. I don't need to say ref suffix, comma, ref n. I could simply say a single ampersand. I still need the brackets because that introduces the lambda. But when I have this is what's known as a capture default. And this says, hey lambda, all of the local variables that I refer to in my body, so this n and this suffix, the compiler sees that they're local variables of main and they're not being declared as parameters. They will be captured by reference. But if I have other things that are not referred to in the lambda's body, for example, v here, data members are not created for them because the lambda doesn't need them. So here this will be exactly the same, it's just shorter. And I can compile and run this, and everything that I referred to is captured by reference, and everything else is not. You can even see this in the debugger. Let's see, I am broken here. So if I look at my locals, I should still have the lambda here. You can see that the lambda has data members, and the, sorry, this may be a little small. The type of the lambda, its implementation specific name is shown here. It's this horrible hash. N is a reference to int, and then suffix is a reference to basic string. But v, which was also local variable, it's not in the lambda at all because I didn't mention it. So I'm not capturing things that I don't need. We can also capture things by value by default. And there, we need to say an equal sign. Although when we capture a single object like suffix or n by value, we just mention the name without anything. We already know that empty brackets by themselves mean a stateless lambda. So the standard says, okay, if you put an equal there, that's a capture default by value. It's not doing assignment, but the notion of equal was similar enough to copy construction that it was considered okay, we can use that symbol. Sometimes in specifying the C++ standard, you can notice that they're kind of desperate for special characters. They've looked all around the keyboard. They haven't quite used the $ yet or the backtick, but there has been active interest in using those characters for other purposes. So if I said equal there, then this would capture everything by value. But look what happens. Here, the compiler is, the IntelliSense is giving me a squiggle around n. And that is because, okay, I've captured suffix by value, I've captured n by value, but here I'm trying to modify n. Lambdas were specified differently than the rest of the language. If you look at how C and C++ are specified, they basically default to everything being modifiable. So if I say int x, x is modifiable by default. I got to say const int x if I don't want x to be modified. If I have a member function and I've declared a whole bunch of functions, and I say int meow pren brace inside a class, that member function is by default not const. So I can modify member variables of my class or my struct. But with lambdas, because lambdas are completely new to C++ 11, and because they're creating separate copies of variables when you capture by when you capture by value, it was considered somewhat confusing to allow their member function call operators to be modifiable by default. Because remember, this is basically stamping out an operator paren that takes whatever your arguments are, const string ref s. So if by default lambda function call operators were modifiable, then that would be strange, because here it looks like we're going to modify the original n, but we're actually going to modify a copy. So the way lambdas are specified is that their function call operators are const by default. Nothing else in C++ defaults to const, but lambdas do. So that means that if I try to capture n by value, I can do that. I get a copy. But because the member function call operator is const, I can't modify the copy. So that's why I'm getting a squiggle here. You can, however, request to remove that constness, and the committee used the keyword mutable. And this is kind of using it for a different purpose than usual. If you say that the lambda is mutable and you put it after the function call operator here, that cancels out that default constness. And now I still capture n by value, but the member function call operator is non-const. So I can actually modify n. It doesn't make n actually mutable. It's specified as removing the constness from the function call operator. So if I do this, and I'll need to, here actually I don't need to show you. Actually I could. I've included string. I could say plus toString of n, like this. Okay, and let me get rid of this. Actually I can leave that assignment there. Okay, so I've made my program increasingly complicated. Suffix was initially an exclamation mark and n was initially 0. I've captured them by copy and I'm incrementing n. And then later I mess with suffix and I say, okay, you're equal to something. So I'm not going to see this concatenated because suffix was captured by copy at this point and it was an exclamation mark at that time. So later modifications don't affect it. And then n here, I'm modifying my local copy. So when I print out n here, it will still be 0 because here I'm modifying the data member. I'm not modifying the original. But I'll be able to see the updates to the data member because I've chosen to concatenate it to my string here. So let's compile and run this and see if we understand the output. Compile and run, and there we go. So now we can make sense of the output here. Let me scroll up a bit and minimize this. Okay, so although I incremented n 5 times, I incremented my copy. So when I print out the original n, the local variable n in main, after the transform, it's still 0. It was unaffected because I modified the data member, not the original local variable. But I was able to successfully modify the data member because every time I invoke the functor, I get cat1, dog2, ox3, and so forth. So I can accumulate state in my function object with a data member like this. I just need a local variable to capture by copy. Now, in C++ 11, lambdas were quite useful, but they were also kind of limited. For example, one of their limitations is that they cannot capture things by move. For example, if I have a unique pointer, I can capture that by reference, and I'll store a reference to the unique pointer. That's totally cool. But if I try to capture it by value, what the lambda will try to do is its constructor will try to copy that unique pointer. And unique pointers are non-copyable. They're movable only. So I actually cannot copy or move construct a unique pointer into a lambda. There's just no way to do it. There's workarounds. You can make like a struct that does hideous, terrible things. Or you could write a handwritten struct that would do the same thing, but then you lose the expressiveness of lambdas. And there's a few other things that lambdas can't do. For example, they're monomorphic. that means they have a fixed signature. I can't make a lambda a template able to accept anything. And this can actually be kind of obnoxious. For example, let's go back to the original transform that I had, where I say, okay, I just have a lambda, and I'm going to take a const string ref s, and then I want to return like s plus an exclamation mark or two. Here I'm specifying something that the compiler already knows. The compiler already knows, based on the type of v, here v begin is an iterator into a vector string, the compiler already knows in some sense that the elements it's going to be operating on are strings. But here I had to specify the type string again, and that's because I can't say, okay, this lambda is just going to be a template, because the lambda has a fixed signature in C++11. In C++14, that has already changed. At the last committee meeting in Bristol in April, they voted in polymorphic lambdas, which I'm still trying to get my head around. But if we look at the latest committee draft of C++14 N3690, here if we go into Lambda Expressions, they now specify all sorts of strange and wonderful things. Let me zoom in here. Here's a generic lambda that takes auto A and auto ref B. This is prohibited in C++11 because you can't put auto there, but in C++14 this is now allowed. And then you can do other things with lambdas in C++14, like initialize their data members with something other than a straight copy or a simple bind a reference. You can have an arbitrary initializer called an init capture, and that's specified as you type an identifier and then like a name like X, and then you could say equal and then initialize it to something. And the committee drafted examples of that. None of that is available in VS 2012, which predates this 2013 meeting, but that's just a taste ahead of what we'll be seeing in C++14. So that's lambdas. I've run out of time, so if you have any questions, ask me in the comments. I'll see you next time.